Okay, time management. This is a graduate course, so for some of y'all, you're going to have to be doing a lot of catch-up or refreshing. So I do expect you to, in addition to lecture, to be reading the book. It'll help you greatly in understanding what we're talking about, especially filling in certain gaps that may not make sense when I'm presenting. You may want to do some weekly exam prep, and then of course your project will be about 5 hours a week if you if you stick to it. Course is on GitHub. I need to update that link because that is not right, and it's also next to impossible to see. All right, it's 2018. The link is on Blackboard. I did put it up on Blackboard. Good. So just go there. If I didn't already add you, just email me. I'll add you to it. Wikipedia has information on microprocessor if you want to, and then Wisconsin actually has a good amount of information on architecture as well. Okay, let's go ahead and at least start talking about the material. Architecture has a lot of different levels of abstraction and are basically different ways to think about what's operating. So when you first have the problem, we usually write it inside of English. Or hopefully we have the idea and it's in our mind and it's probably some type of English as we try and explain it. We might come up with a solution and write a pseudocode, which you do every time, right, Matt?
No.
Wow, honesty. And then you take your pseudocode, you might translate it to C or Verilog or maybe Java if you feel so inclined. And then the compiler will translate that into assembly instructions or OS calls. And then an assembler will change that over to machine instructions. Then your processor or your microarchitecture is how you think about you're going to design or implement those instructions. Then the gates and flip-flops are a basic schematic of how you would implement it from a logic level. And then from a circuit level is your transistors and sizing of how you would actually implement the gates and flip-flops. And then at the very bottom is when you'd have the physical transistor layout, maybe how size of your transistors, and then how will you connect them with cables, and of course your PC boards. So there's different ways to think about your problem. I mean, you could sit down and think about how you would etch every transistor into it, but most people don't do that. They're usually a little high level, but depending on where you are in the industry is where you're thinking about it. What are the abstractions each level? I went through that. Okay. At what level do I perform a square root? Ooh.
Do you? Who is you? Who is I?
That's a good question.
Is I you? Because you would probably use an algorithm.
Yeah, I'd use it. So yeah. Right, I'd use an algorithm to do it. Good. What about the computer?
It would probably be on the. That's kind of tricky.
It is a little tricky.
Yeah.
Probably the very bottom. Right?
Yeah.
Because what's all this in between?
Getting there.
Getting there, right?
The code.
So you see that our idea is up here. It's really in English, and we're pretty good at putting pseudocode and writing it in C. After that, we basically ship it off to some program, which eventually translates it to the physical layer for the computer to actually implement it. All right. How about recursion? Oh, here's a good one.
That depends.
Oh, I love the answer. All right. What do you mean?
I mean, like, technically it could go all the way to the bottom.
Yeah, at some point it goes all the way to the bottom.
But still, you're going to have, like,
but assembly is doing a lot of
the stack.
Yeah, the stack and the machine code. So. But you have to also design it microarchitecturally as long as logic and gates. So, yeah, I mean, recursion is happening all over the place. But you're not. Well, you might write it in your algorithm, right?
Be a short algorithm.
Be a short, nice, short, beautiful algorithm, right? Yeah, so there's different ways to look at it. Where are you coming from? Oh, here we go. Who or what translates from one level to the next? Who goes from English to pseudocode?
Nerds.
Nerds. Nerds? I like the answer. Who goes from pseudocode to C or Verilog?
Programmer.
Right. Different than nerd. Well, not maybe a nerd, may not be. All right, who goes from C to assembly?
The compiler?
Yeah, that's the compiler. Who goes from assembly to the machine language?
compiler as well, wouldn't it?
We think of it as the compiler, but it's actually not it's not the compiler, it is the assembler slash linker. Usually we think of it as the compiler because we usually bundle those two together, but it is a very separate step.
The old days. where they were
Yeah, you
separate.
have. Yeah, they are actually still separate inside of GCC as well as Clang. It's just that when you run GCC, it automatically calls everything for you. But if you look up what GCC is, it's basically a script to first compile it, run the assembler, run the linker, depending on your flags. So it's still all done. It's just more of it's automated for you. All right, here we go. Who translates from the machine instruction to the microarchitecture?
The hardware?
The hardware. Who organizes the microarchitecture?
Now the processor.
So that's on the processor, yes, kind of. But the processor is really just this thing down here.
Would be the operating system?
That's
It is the processor. I would take the processor as an answer actually for this one. Who designed the microarchitecture? Let's start there.
well, that's kind of part of the processor design, right?
Yeah. So, well, was it a programmer?
Yeah. Okay.
Well, probably not.
Engineer-
It was an engineer. Yeah, it was a different engineer. It wasn't a programmer. He's the one doing pseudocode to C.
Right.
Now we have an EE guy, or possibly.
Whoever's designing the processor. Right?
Actually, this is the
You-
architecture, right? This is the
Yeah.
computer architect is what this is. Computer architect does this part. How's the microarchitecture to flip-flops go? Ooh, this is a hard one.
Wait, so we said the CPU for the...
For machine to microarchitecture, I will take the CPU, but
Okay.
in reality, it's the computer architect is defining, here are the machine instructions, how do we design the microarchitecture, how do we organize it with block diagrams? That's the architect, the computer architect's doing that. But once he's done that, what makes the gates and flip-flops?
Well, isn't it the same designer?
So back in the day, the 60s, yes, definitely.
Would some program do that for you?
Yeah, so some type of hardware description language. So Verilog or VHDL does that for us now. And really it's to go from here to here, that is the name escapes me.
From logic to circuit?
Yeah, no, from here to here to the flip-flops, it's not the synthesizer, it's, I forgot, it's part of the, it is part of the Verilog, but from logic to circuit level, it is the synthesizer, and then circuit level to the last one is the layout. But all these three are now automated. So, the point of this is, where's the human? Problem and idea, down to algorithm to high level. So that's the human. Then you have computer, machine, and then right here you have another human designing the microarchitecture. And then down to logic and whatnot, it's back to machine. So
So the circuit level and the physical, right there. I'm trying to understand the difference between those two guys because you're getting down.
okay,
The VLSI is actually on your circuit board.
right.
Right.
Let me
And
try to
your
help you out.
transistors are still on the drawing board, right?
Right.
Is that
So
what you're
you
saying?
might have, let's see how to put this. I forgot how to draw a transistor. What was the symbol? I always forget it. We'll say this is a transistor.
It's just been so long.
So here's one transistor,
Mhm.
but as modern processors have about 1.4 billion of it. Microarchitecture to the logic level tells you how one transistor is connected to another. Okay? Like this one needs to connect to that one needs to connect to this one. From circuit level, the transistors to the physical is where do I put each one of them? Because you want, if they're connected together, you probably want them physically close to each other. But you have to also keep in mind that there's the speed of light as the upper bound of how fast, So this one you really got to sit down and lay out. Now, I did say this was automated with the machine. I kind of halfway lied. There are people who sit down and literally do layout all day long.
So that's your diagram kind of like you're doing with your logic level. You've got all your
Yeah, but now you have all your transistors and you know what they need.
Transistors, and it's all drawn out, and then all of a sudden you put it actually on
Yeah.
a circuit board where they're
Yeah, you gotta lay it. Yep, where they
solid or
are.
whatever.
Yeah. Burning them. Alright.
So it's machine level, but it's not actually the machine yet till it gets down to the very bottom.
Right, that's the actual CPU. Okay, so the architect, which is what we're talking about, computer architecture, we're looking basically at this level most of the time. For the purpose of this course, I don't think I'm going to talk about the bottom anymore. That was more in computer architecture, so hopefully you've had at least some architecture there.
I'm a master of that.
But because these lower three levels, logic level, circuit, and physical, that's usually for an electronic engineer, an EE degree. So you want more than that, take that major. But we're going to focus mainly between machine and microarchitecture because we're computer architects. So you can kind of think of it as there's software guys we have to talk to, and there's the hardware guys we have to talk to, and they don't necessarily have the same idea about things. All right, so yeah, we're responsible for the specification, the instruction set, the microarchitecture design, and who do we interact with? Well, the compiler, because remember that's above us, and then the logic level designers, which usually is a computer, but someone has to drive that machine and figure out how to do layout and whatnot. We can't do a good job without both sides. So we need to know what software our programmer's writing and what hardware are hardware people able to make. So we have to balance both of these. All right, some design issues. First one is performance. No one likes a slow machine. Getting acceptable performance out of a system. So first off, we always look at what is acceptable. So for scientific, a lot of time it's floating point, memory and disks, but it's also very predictive. We're gonna do fast Fourier transfer. We're gonna do matrix multiplication. We know what functions are gonna be called over and over again. So if we wanted to build a processor specifically for scientific notation, we probably have some hardware circuitry to do those as quickly as possible. Commercial, like banking software, websites, a lot of string manipulation and string handling, a lot of interfacing with disks or databases. Again, it's predictable somewhat because you know you're going to be handling strings and whatnot. Multimedia ones, so video, but it could be other things as well, audio, usually on a network. Fortunately, it's not always predictable because even a video stream may need a lot and need a little all of a sudden. And you may not know which codec is the most popular one all of a sudden because that does jump around. So multimedia can be unpredictable at times. Embedded. What's the performance requirement of embedded, aka your phone? This is a trick question, in a way. What characteristics of your phone do you care about?
Texting.
Texting? Does that require a fast processor? No. What's a different metric you actually care about?
Netflix.
Netflix, okay. So does it have enough to actually stream?
It's just the versatility of it.
Versatility.
You can do so many things on it.
So the reason why I said it's a bit of a trick question is so far I've been calling performance how fast it runs. But there are other performance metrics. What do you care about your phone besides how fast it runs?
How long it runs.
Reception's a good one, or how long it runs, which is based off of
The
battery and how much power is consumed. So battery performance is actually what you want in an embedded system. There's some trade-offs there because if you put the clock down, maybe make a couple other architecture changes, your execution speed performance will go down, but your power performance will improve. And then lastly, workstation. Well, it depends on what work you're doing in front of you. I mean, if you're doing a lot of CAD designs, you probably want a good GPU in there. But if you're just doing a lot of spreadsheets, you don't need a giant GPU for that, right? So it really depends. So big point here, there's trade-offs depending on your audience, and also there is no one-size-glove-fits-all. We don't have a silver bullet. Okay, how do we calculate performance? Usually, execution time is often the best metric that we care about, and that's what we're going to talk about most of the time. Yes, power is important for our phones, but most of the time in architecture, we're thinking about performance. How can we decrease the execution time as much as possible? The first big thing is throughput, tasks per second versus latency, which is seconds per task. When would one be more important than the other?
If you have to multitask.
You have to multitask, so that would, which one would be important? Well, maybe. Depends, actually. I don't know if multitasking would be exactly.
Latency would be bad if you wanted a task to be done fast, but it takes a long time.
Right, what instance would that be? Netflix. Okay. Well, I mean, if your movie starts 1 second late, does that bother you that much?
No, but if the sound's 1 second late.
Well, that's something different. That's something different. That's a software bug. But latency in that part would be your movie started 1 second late.
Well, if you like click an icon on your desktop, you don't want the lag. Or if you click like the X, you don't want the lag.
True. What type of user situation is that? Getting a lot from Matt. So yeah, latency, how fast the task is done. Throughput, how many tasks can you get done per second? Which sounds like which? So latency, you said, what were you saying with latency? You're saying something about clicking on the desktop?
Yeah, and it being delayed.
Okay, how many users are there of that system? One. So you have one user, it's probably all about latency. So hint, hint, when would you have a lot of users? Throughput. In what situation?
A game server.
Server.
Yeah.
So anytime you have a server, you're more concerned about throughput. A game server, we'll get back to that. But if you're serving a web page and it might be 0.2 seconds slower, but your throughput doubles, that might actually be an acceptable trade-off in that regard. And so a lot of server chips are built to handle a lot of threads or a lot of pieces of execution at one time, while a workstation is all about single thread performance. How quickly can we respond to something? Okay, and what do we use? So bullet 3, what do we use in order to calculate these? Well, we use benchmarks. What are the tasks? We literally just take the benchmark we want and go ahead and execute it. So we usually try and come up with some representative program. There's something called Spec and LenPack. LenPack's really good for testing scientific stuff. Spec is very good if you want to do a workstation type environment. We call something called kernels. This is not the Linux system kernel. A kernel here is a small snippet of code that represents a code fragment that you expect to be run a lot. You might have some toy programs. This is very popular for game test benchmarking. You know, what frame rate do you get in Crysis? Always a good one. And then synthetic, sometimes you just throw a bunch of instructions together and see what happens. Okay. Another performance or design issue. So we talked about execution. We've hinted on power. Another one is cost. And many different things can affect this. First off, the die size, aka how big is that processor? What type of packaging are you using? Does it have a lot of connections coming out, or is it going to be a very simple one? Do you need a heat sink for this thing? That always costs more. Do you need gold connectors?
Yes.
Yeah, you always need gold. Really need that conductivity. So yeah, you need support. You're going to have a fan. Or you're going to have to be water cooled. What motherboards are going to support this? Does the motherboard have to be expensive in order to support your processor? The big thing is here. Calculating the actually processor cost, it's the die cost plus the packaging, plus whatever you have to do to test it, because they are tested a lot, divided by the yield. The yield right here is to represent the fact that when you create a bunch of these, some of them are going to be thrown out as bad via testing, so you're only going to get so many of them. And that, of course, as you have a worse and worse yield, that increases the cost. So if everything was perfect, yield would be 1. If you have a 50% yield, 0.5, which of course doubles the cost. Okay, so how do we figure out the die cost? This guy right here. Usually packaging is pretty straightforward. You drop the chip in, has connections, make sure they're soldered. Testing, you know how much it costs to test those with your different machines that you've probably come up with. Die cost, the wafer cost divided by good die yield. So good die yield related to the die size and defect density. Defect density here is what's the purity of your silicon that you're starting with. Lastly, there's support cost. The direct cost, aka the components to make the processor, the label to make the processor, and then there's indirect cost, which is costly. You have to have salespeople to advertise it, service when there's problems, and then and then research and development. You know, you got to pay people to actually design these things,
Or just sell off your stocks.
or just sell off your stocks really fast. Lastly, your total cost is always amortized over the number of systems sold. So for example, if you're doing a personal computer, you're probably going to sell a good number of them. If your only customer is NASA, you're not going to be selling too many units, right? So that'll probably affect what your cost of your chip is. All right, other things. We talked about power. For example, NASA, you'll have a deep space, so it's all about reliability. They'll actually do into a lot, yeah, there it is, radiation hardening. So that's a different level of requirements for your hardware and software. AMD, they're not the authentic x86, so they're all about code compatibility, which they actually do pretty good. ARM is what a lot of our smartphones are running, so their concern there is power, which has actually become a very big topic nowadays. Okay. I didn't put this up here, but I do like to ask this. Have y'all seen any news about computer architecture recently?
Nope.
None at all?
No.
If they could do anything.
The thing with the processors.
The thing with the
massive
processor.
flaw.
Massive flaw in the
Yeah.
processors. Okay.
Who knows?
Who knows?
Probably no glaring security holes. Trying to cut corners.
Who would do that?
Not Intel.
So if you haven't looked at Meltdown and Spectre, where are we? This came out fairly recently, a month or two. It is an exploit in modern processors. This is actually a huge one.
Oh, wow.
Yeah, it's a hardware allow programs to steal data which is currently processed on the computer. I think the video for this, the second video, really showcases this extremely well. Go down to here, boom. All right, so down here at the bottom, he's going to run a program, and this is the example of the rogue program. And we're going to say that this is a normal user application. So someone's just running a normal user application on your machine. Can easily happen to anyone who has access to run something. Up here represents another program that maybe someone completely different is running. Maybe they're logged into the same machine and they're running it. Well, the first thing they need to do is put in a password, right? Well, when he puts up there, goes up here, starts typing his password, the other machine can actually gain access to it via Meltdown on certain machines and be able to print it out. And this doesn't just apply to passwords, anything that's being stored, credit card numbers, etc., etc. So what is actually going on here? What's happening with Meltdown breaks the fundamental isolation, this is actually huge, between user applications and the operating system. Normally the way protection's done is you have a user application that's running, and then in order for it to access a piece of memory that's out of bounds, it has to interrupt the, you have a user application. Inside the hardware, it fixes what bounds you're allowed to execute or to access, and the processor is what stops that. It's a hardware support. What this does is basically get around the bounds checking so that you can just access any piece of memory that's on the system. Which means if another system is holding memory with your password currently in it, or your credit card number, you can now read it. And that's what Meltdown does. Currently, they're trying to figure out how many processors this affects. The current thought is it affects every Intel processor made since '95. I'm still going through the paper, but right now, it looks like what it is they utilize out-of-order execution, which we are going to talk about in this class, in order to access pieces of memory that are outside their bounds. They actually pull it into the cache via the way caches work, and then later they get interrupted and they're able to come back and then read the caches due to a couple of tricks. And that's Meltdown. AMD has confirmed that they are not vulnerable to Meltdown. So Intel's in trouble. Spectre works similarly, but it's a lot more complicated from what I've read. I haven't started reading this one yet. AMD is still trying to determine if they're vulnerable to Spectre, which is going to do something very similar. ARM, again, making the chips on your portable devices, has confirmed that all their Cortex A7s through A9 are vulnerable to this, to Meltdown.
Maybe I should have upgraded.
There is a software patch for this, but it slows down your machine. So, we're going to see how this turns out. This is still fairly new. I'm going to see tracking, see what's going on.
So the person has to have access to it before they can.
Right, they're going to run a program on it. Now, the program doesn't have to be a root program. It is a standard user program. It's not a...
But it still has to be on the machine.
Well, yeah, think of this as a server, right? You log into a server, you log into servers all the time. You're now allowed to do certain things. You run a program on that machine as yourself, which you should have permission for. You can now look at other people's connections. So, there's still at least that level of security, but, that's not much. That's not much. Luckily, when they released security people are at least smart about this. When they release these big things, they always say, by the way, here's the fix. So not everyone can immediately do it. So hopefully all our server machines are going to get this placed on ASAP. Okay. So I guess you haven't looked into it. Any questions? Actually, here's the real question I have for y'all. I said the software thing slows it down significantly. What would have to happen in order to get around that? Who has to fix it?
The hardware guy.
Intel has to fix it. Now, how do they fix a hardware problem? Redesign the chip, and then for your end customers, what do you have to do?
Buy a new one.
Yes. You have to go and get a new piece of hardware. You cannot, this isn't like a software update to fix a hardware issue. You have to physically go in and replace the hardware. So it's far more costly to fix a change here than a software change.
I just bought a new computer.
I want a refund.
Well, it has an Intel in it?
Yes.
Yep. Yeah, this is going to be interesting because AMD released they're not vulnerable to this one, which is the apparently the easier one to take advantage of. They're trying to still determine, this guy's a little tricky on how he works, so they're still trying to determine if they're vulnerable or not.
Raspberry Pis, they safe.
Yeah, do they have a Cortex A7 or A9? I
They're
don't know.
just safe. I read that on the internet.
Okay. Wow.
So it's gotta be true.
Well, yeah. All the truth and lies are on the internet. Okay. All right. Quantitative. Let me pause.